For our final example, we have a small lamp clamped on a fixed circular bar at C. The assembly consists of two pieces connected with a torsional spring employed to promote the clamping of the jaws at A and B on the circular bar at C. We are asked for the minimum moment the torsional spring at D must produce so that the lamp does not slip on the bar. It should be clear from the eccentric center of gravity that the assembly, if it slips, will rotate clockwise about the center of the bar. But where does it slip first, at A or at B? We will examine two cases employing consistency checks in both cases similar to what we did for example 1. So for the first solution, I'm going to assume that slip occurs at B on the right-hand side of the bar C. And we're clamping this bar. This way I'll make this normal force at B, normal force at A. And if I'm slipping first at B, then as this tries to slip, this will be the friction coefficient times the normal force at B. I have a friction force at A, which has not reached slip yet. And then I will allow this, somewhere in the background here, I'm going to allow this bar to have reactions or to be built in. So I think I'll sketch this in a different color just to indicate that. So these green colors are going to indicate that somewhere in the background of the screen this bar is built into someplace, and therefore it's got a CX and a CY and a moment. Now we won't actually need to examine the equilibrium of the bar. After the fact, we could figure out what those green reactions are if we wanted. We're just going to focus on the other two pieces of the assembly. So we'll have equal and opposite forces at B. We have a pin at D. We don't know what direction these forces are acting. I'll call them dx and dy on this side. And then we have the torsional spring, which is trying to clamp the bar C. So that on this side, it will have a clockwise moment. I'll call that M subscript T for torsional spring. And over on the other side, then, we'll have a dx and dy equal and opposite, and then over on this side, the torsional spring is exerting a counterclockwise moment. And then we have the forces at A. We have equal and opposite to what's below. So we have NA this way, and we have FA this way. And one more thing, I forgot the weight at G, so let's put that in. Okay, so those are our set of free body diagrams. And then our consistency check will ask if the ratio of the friction force at A to the normal force at A is less than the coefficient of friction. Now if we confine our attention to just the two pieces above and not worry about the bar at C, you'll see we have a total of 6 unknowns. We have the normal forces NA and NB, the friction force FA, the pin reactions dx and dy, and the torsional moment exerted by the torsional spring. So by looking at these two free body diagrams for this one at A and this one at B, we should have enough information to solve for the things we don't know. So I'll actually start on the right with 2, and I'll write some of the moments about D equals 0, and also some of the forces in x equals 0, and some of the forces in y equals 0. So take some of the moments about D. Given the information in the problem statement, I'll use meters instead of millimeters. We have the normal force at B times a moment arm of 0.025 meters. I'll leave the meter designation off. I'll understand that all the distances are in meters. Then we have plus the friction force, mu NB, times 0.015 meters, minus the moment due to the torsional spring, minus the weight times 0.08 meters equals 0. And in x, we just have the normal force at B minus dx equals 0, And in y, we just have the friction force at B minus dy minus the weight equals 0. We'll call these equations 1, 2, and 3. For the free body diagram of A, I'll again write some of the moments about d equals 0 and combine these with force equilibrium at x and y. We have the moment from the torsional spring minus the normal force at A times 0.025 meters plus the frictional force times 0.015 meters equals 0. And we have dx minus na equals 0 for force equilibrium in x, and we have dy minus fa equals 0 for force equilibrium in y. We'll call these equations 4, 5, and 6. Now, in spite of the fact that we have 6 equations, this problem is simpler than perhaps it first appears. We can put different combinations of these together to get to the solution relatively quickly. So I'm just going to note that from equations 2 and 5, we have dx is equal to na is equal to nb. So the normal forces clamping the bar are the same and equal and opposite. From 3 and 6, we have that the force at A is equal to dy. So we can take that information and put it in the equation. So we can take that information and put it in equation 3, and that gives us Fa is equal to mu times the normal force at B minus the weight. Now, before we continue, this is actually very encouraging because we were going to eventually employ this consistency check to be sure that we satisfied our static friction criteria. Note that the ratio of Fa to Na is equal to, since Na is equal to Nb, this is going to be equal to the static friction coefficient minus the ratio of the weight to the normal force at A. But we'll go ahead and carry through the details just to check it out. Okay, so now what I'm going to do is I'm going to take equation 1 and add it to equation 4. If I do that, note that the torsional spring cancels out here and here, and the effect of the normal force, because Na is equal to Nb, this will cancel this, and what we'll be left with is static friction coefficient times the normal force at B times 0.015 minus the weight times 0.08 plus the friction force at A, which we now know is mu times the normal force at B minus the weight times 0.015 equals 0. So that allows us to solve for the normal force at B. In fact, if we rearrange this, we can find that the normal force at B is equal to 0.095 times the weight over 2 times the static friction coefficient times 0.015. This turns out to be equal to 5.278 times the weight. And for a mass of 1.6 kilograms, this number turns out to be equal to 82.84 newtons. And we'll just check. Once again, we have our ratio of friction force to normal force is the static friction coefficient, which is 0.6, minus the ratio of the weight to the normal force at A. And since the normal force at A and B are the same, this is 1 over 5.278, and that's 0.411. So obviously we're less than 0.6, and then this is consistent with our constraints on friction. Having obtained these results, we can now substitute back into our first equation and solve for the moment of the torsional spring, and that's 82.84 newtons times 0.025 meters plus 0.6 times 0.015 meters minus the weight times 0.08 meters, and that result gives us a torsional moment from the spring that's equal to 1.561 Newton meters, or 1561 Newton millimeters. Now that is the correct result, but just for completeness, let's take a look at the other case where we assume we have slip at A. We'll draw the free body diagrams and be able to tell relatively quickly that that in fact will not be consistent with our expectations. So I'm just going to redraw these free body diagrams now, assuming that the slip occurs at A instead of B. So here I've redrawn the free body diagrams. Everything is the same except for slip is now shown to occur at A instead of B. My check is that the ratio of the friction force to the normal force at B be less than the coefficient of static friction. Once again, I'll write equilibrium equations for the right portion of the assembly first, and those equations now look like this. You can compare these equations to what we previously generated for the first solution, and you'll notice the only terms that are changing are this one and this one in the free body diagrams for the right piece of the assembly, and this one for the left piece of the assembly. Once again, we can solve these relatively quickly. If we take 2 and 5 together, we have dx equals NA equals NB. That's exactly the same result as what we had before. From 3 and 6, we now have that dy is equal to the product of friction coefficient and the normal force at A. So we have from equation 3, we have the friction force at B is equal to dy plus the weight, which is equal to mu NA or mu NB plus the weight. And now we see we're going to run into trouble because our premise is that the ratio of the friction force to the normal force at B is less than mu. And what we have here is the ratio of the friction force to the normal force at B is equal to mu plus the ratio of the weight to the normal force at B. So we could go ahead and continue this solution if we like, but we're going to get essentially that this is some positive value, and we're going to find that this is greater than the static friction coefficient, so this doesn't work and it's not consistent. Therefore, our first solution was the one that we wanted, and if we go back up there again, we have that our torsional spring had to exert a moment of 1561 Newton millimeters. So what you've been able to see from these two examples is that these problems are not necessarily more complicated, but they have branches, and each branch requires a certain amount of work. So there's just a lot to keep track of when we have the possibility of slip occurring at more than one contact surface.